In this lecture, we consider the motion of a quantum particle of mass m under the action of a potential this, where the potential is minus lambda by x in the positive region, and it is infinite on origin and to the left. That is, the particle is confined to x positive region, and the potential that acts on it is varies is an attractive potential and varies inversely with the distance. This is just a Coulomb potential, attractive Coulomb potential that acts attractive potential between electron and proton is V is equal to minus E square by 4 pi epsilon 0 r, where r is the distance between electron and proton. This potential exactly is of this sort, only the fact is that it is a three-dimensional potential, spherical symmetric potential. It is the one-dimensional analog of this. So we have to find out the quantum mechanics of it. One thing is that since the potential is infinite at x is equal to 0, whatever the wave function we will have, the boundary condition to be satisfied is that psi of x is equal to 0 and psi x tends to infinity must tend to 0. These are the boundary conditions, because the particle is bound by the attractive potential, so it cannot fly off. The Schrodinger equation, time independent Schrodinger equation, is minus h line square by twice m and as we are considering bound state aspect, E has to be negative, so we write it psi of x, where for bound state E is negative, so we write E is equal to minus epsilon, where epsilon is a positive quantity. Or this equation becomes h line square by twice m del 2 psi del x2 plus lambda upon x psi is equal to epsilon psi. The calculation can be simplified by introducing dimensionless variable, and we use a scaling, rho is equal to alpha x. We can scale any quantity by this is alpha is called a scaling parameter, and any alpha value other than 0 and finite can be acceptable, and the choice of alpha is left to the user, so and one chooses alpha in such a way which simplifies the calculation. So the derivative del ddx now becomes del rho del x del rho, and it is in one dimensional case this is alpha dd rho. Similarly, we will have d2 dx2 is equal to alpha square d2 d rho 2. So if we plug this in this equation, we will have h line square alpha square by twice m d2 psi d rho 2 plus lambda x is equal to rho by alpha, so it is lambda alpha by rho psi, and it is epsilon psi. Or or we write this equation as as we have pointed out earlier that the choice of scaling parameter is entirely in our discretion, and we can choose any value of alpha other than 0 and infinite. We choose alpha in such a way that this is 1 by 4. So we choose scaling as that 2m epsilon by h line square alpha square is equal to 1 by 4, or alpha square is equal to 8m epsilon by h line square. And beta, we have introduced beta. Beta is equal to, actually this factor we have introduced as beta. This is beta, and so beta is equal to, so if we use the value of epsilon with square root, from there it will be 2 square root 2, so this cancels with 2, so we will have lambda by h cross, and this is m by twice epsilon. It is the value of beta. So the equation now becomes, the equation simplifies to if we try to solve this equation by Provenance method, we will find the problem is complicated. Rather, some clue may help us in finding the solution. The clue is that what is the asymptotic behavior of the wave function? Asymptotically, that is when rho tends to infinity, the wave function is A for asymptotic, which gives you a solution. But e to the power plus rho gives you divergence as rho tends to infinity. So the physically acceptable solution is acceptable solution which satisfies this boundary condition. The plus sign doesn't satisfy this boundary condition. So what we have done in nutshell is that we have transformed this equation in terms of rho, and if you calculate the dimension of rho, you will find it is L inverse. So if this is if you calculate the dimension of alpha, it has rho L inverse. So rho is actually a dimensionless variable. So rho is dimensionless position. As check it. Check it. So we have transformed this equation for the bound state into the dimensionless form, this where the scaling parameter alpha is defined like this and the beta is this, and the asymptotic behavior of the equation is this. So we keep the summary over here. This equation now becomes zero with rho is equal to alpha x. Alpha is equal to alpha square is defined as 8 me, the bound state energy, by h line square. Beta is defined as lambda by h cross m by 2 epsilon, and the asymptotic behavior is rho by 2. This is the summary that we have done here. Actually, this asymptotic solution is the solution of this equation. So if we want to find out the solution of this equation, the solution for all rows, so for rho greater than 0, the solution, we write solution as some function f of rho multiplied by e to the power rho by 2, such that with rho tends to infinity, f is a constant, f tends to finite value, and as rho e to the power 0 is 1, we will have another condition that f of 0 has to be 0. This is the condition. See, let me repeat once again. We have found that the asymptotic solution is of the form this. So the general solution, which is valid for all positive rho, must contain this factor together with a function rho which is yet to be determined. The boundary condition that psi of rho tends to, as rho tends to infinity, is 0. Indeed, as rho tends to infinity, this quantity tends to 0. So that total quantity will tend to 0 provided f is finite. So f is finite as rho tends to infinity, and at rho is equal to 0, the wave function has to be 0. This at rho is equal to 0, this is 1, so this must be 0. So these are the two boundary conditions to be satisfied by f. Now we rewrite this equation, this differential equation, as before we substitute this trial solution into it, so that we will have rho prime is equal to, first we differentiate this, so this is f prime, this remains fixed, and when we differentiate this, it is half f to the power e to the power minus rho by 2 and f double prime, sorry, psi double prime. First we differentiate this, so this is f double prime minus half f prime multiplied by this, and secondly when we differentiate it we will have half and then prime minus 1 by 2 f, and whole thing is multiplied by e to the power minus rho by 2. If we simplify this, we will have f double prime minus f prime plus 1 by 4 f whole to the power multiplied by e to the power rho by 2. If we substitute this and this equation, what we will find? Together with this and this. So for f double prime, phi double prime, this part e to the power rho by 2 part is with everyone, so we discard this. Then we will have this part beta by rho. We have neglected the e to the power minus rho by 2 term, which is which is to be multiplied by all this. So this is f double prime minus f prime. You see that these two gets cancelled, plus beta by rho f is equal to 0. If we multiply all the sides by now the problem of solving the quantum Schrodinger equation for the particle has reduced to the solution of this differential equation. So the problem is this, we initially have this equation which I want to solve for bound state problem. The solution has now reduced to the solution of this differential equation with f and phi are related by this defining equation. So again, as the space problem, I only write the relevant parts, and we will have rho f double prime plus minus rho f prime plus beta f is equal to 0. See that rho is equal to 0 is a so if we apply Provenance-Fuchs method, the solution of this differential equation as per Provenance Fuchs theorem, the solution is f of rho is equal to sum over k is equal to 0 to infinity ck rho to the power s plus k with c0 not equal to 0. As you are habituated, you are familiar with Provenance method. I am just skipping steps. If you differentiate these two times ck s plus k s plus k minus 1 to the power s plus k minus 1, this is the contribution of this term, on differentiation power is reduced by 1, and when you multiply by this the power is again raised by 1. Initial equation. That is the coefficient of s to the power rho to the power s minus 1. This term only contributes with, since C0 is not equal to 0, the solution is s is equal to 0 and 1. We know that whenever the roots of the initial equation differs by an integer, it is guaranteed that the higher root will give you a solution, the lower root may or may not give you a solution. Keep it in mind. Recursion relation. We use rho to the power s plus k. The coefficient, we equate the coefficient of s plus k. From say left hand side we will have k plus 1. This term is s plus k because k has to be replaced by k plus 1, and this is s plus k plus 1. And on the right hand side we will have ck s plus k minus beta. So ck, again ck is coming, k plus 1 is equal to for s is equal to 0, this becomes, I think this portion of the board is visible to you. Let me check first. Yes. For s is equal to 0, we have ck plus 1 is equal to k minus beta by k times k plus 1. If you want to find out C1, for C1, determination of C1, you have to put k is equal to 0. So this C1 is not obtained. C1 cannot be obtained. So we see that for s is equal to 0, the series cannot be generated. That is the statement of second Frobenius-Fuchs theorem, that the lower root may give you a solution or may not give you a solution. It is the situation when the lower root does not yield a solution. So the acceptable s value is s is equal to 1. So we come to, again, the conclusion is that ck plus 1 is equal to, s is 1, so k plus 1 minus beta by the, in the denominator it is k plus 1 times k plus 2 ck with s is equal to 1. So we get the solution of the equation by using Provenance method. Since this solution is an infinite series solution, one must check the convergence. So the for convergence, the ratio test for convergence you will have rho to the power s plus k plus 1, that is s is 1, so we write it k plus 2, and in the denominator if we use this relation, it becomes k plus 1 minus beta k plus 1 This can be written dividing both numerator and denominator by k square. It is 1 plus 1 by k minus beta by k. This is 1 plus 1 by k. This is 1 by 2 by k, and it is rho by k. We divided both numerator and denominator by k square. One k is here, another k is there, and obviously as k tends to infinity, for very high, its behavior is rho by k. At first sight it may seem that it is a convergent series, but I go to the comparison test. For x to the power m e to the power x with any finite m, we have same asymptotic relation. That is, the two consecutive term has the same behavior. So it is found that asymptotically the solution of this problem is similar to a non-divergent series. So the series is divergent. But if we want to find out a physical solution that must not blow off asymptotically, then what we need to do? We need to choose a special value of beta so that the series gets truncated after certain term. So we choose a value of, since the numerator it is integer, this is integer, if beta is chosen to be an integer, then there will be certain terms, certain ck's, and afterwards all ck's will be 0. So for truncation we choose beta to be n. Here quantization takes place. If we use beta to be n, then the relation becomes ck plus 1 is equal to k plus 1 minus n by k plus 1 into k plus 2 ck. And if we calculate, that shows you that Cn is n minus n, where this is n into n plus 1, Cn minus 1 is 0. So for beta is equal to, and all other higher Cn's are 0. So for beta is equal to n, the term that survives is C0, C1 up through Cn minus 1. So there are n terms. If we come to the energy eigenvalues, now you see the energy eigenvalues is given by this. Now beta is equal to n is equal to lambda by h line root over m by twice epsilon. This is this relation. So we get En is equal to, if you square it, so it is n square h line square n square h line square or epsilon n the energy eigenvalues goes as 1 by n square, exactly as we found in the case of Bohr's theory. The energy eigenvalues goes as 1 by n square. Similar thing we have obtained here in this case. Coming to the wave function, if we want the ground state wave function, the ground state wave function is obtained for n is equal to 1. So for ground state, we have n is equal to 1. In that case, the solution that is we obtained has only one term, C0. So f of 0 of rho is equal to rho to the power s times C0, and the corresponding phi 0 is equal to C0 rho e to the power minus rho by 2. And for first excited state, we have n is equal to 2. So the it is f1. So f2 will have two terms. f2 is rho to the power s, this C0 plus C1 rho e to the power minus rho by 2. So it will have two terms. Oh, sorry, this is f, this is f. N is equal to 1. Rho by 2. You see that consider this wave function. At rho is equal to 0, this is 0 due to this factor, and as rho tends to infinity, our function is 0 due to this factor. Similar thing is that all the wave function has is 0 at the origin and 0 becomes 0 asymptotically. If we plot this wave function at small values of rho, for small values of rho, this part is almost 0. So initially the graph increases linearly, but as rho increases, this part starts dominating. That is, it will decrease the wave function and it will go to 0 asymptotically. This is the plot of psi 1 versus rho. Here we have adopted a problem, the method which is very involved and is generally used for finding out the eigenvalues, energy eigenvalues, and wave functions for general problems in quantum mechanics. You will see that in harmonic oscillator or as well as in hydrogen atom problem, we will exactly follow these steps. The step is that first to convert the differential equation in dimension form to dimensionless form. So this is by using a suitable scaling parameter. Then we will study the special behavior of the wave function, that is either asymptotic behavior. In the case of harmonic oscillator, we shall find that the asymptotic behavior is sufficient enough to land up into a result, but for the hydrogen atom problem we will find that the only asymptotic knowledge does not work, so we have to also find out the near origin behavior, and then we go for a solution, trial solution, and we will impose the condition of on the unknown function, which is most likely a polynomial function, and we will find out the differential equation for it and check for the solution convergence of the infinite series solution. And we see that for the convergence the series has to be truncated, which leads to the quantization and the quantized energy values, and the wave function will be obtained. This is a very simple problem of the general category that we have considered here. But this problem can also be solved if our aim is to find out the ground state wave function and the energy. We need not to go through such a complicated procedure. We can find out the solution for most simply from physical reasoning. So we are going to present a physical treatment which enables us to find out the ground state energy, M. Ground state energy. This is the problem. Then we say that the wave function corresponding to ground state must be in x e to the power minus some gamma x. Because the wave function has to be 0, this is ensured by the presence of S factor, and the wave function must be 0 asymptotically. This is satisfied this function. We use these in this equation. So we have on simplification, this gives you n times gamma square x minus 2 gamma e to the power minus gamma x. So we plug this into this equation for ground state. This equation for ground state becomes, this minus sign goes, h line square by twice m pi 2 double prime gs plus lambda by x gs is equal to epsilon gs. Oh. In and e to the power minus gamma x is common all over. Coming to this factor, from gs you will have an x which cancels with this, so this is lambda only. For this we will have now this equation has to be satisfied for all values of x, that is x to the power, the coefficient of x to the power 0 is minus h line square by m gamma plus lambda is equal to 0, and x to the power 1, the coefficient of x to the power 1 gives you h line square gamma square by 2m is equal to epsilon. So we need to replace we need to replace gamma from this equation. This is GS energy, sorry, ground state energy. And for gamma square we write m square lambda square h line to the power 4, so it is m lambda square you check that epsilon n, we obtain m lambda square by twice h line square n square. For n is equal to 1, this is the result. I must thank Professor Partho Ghosh, your PG sir, for suggesting me this problem a few years back.